Continuing 5.4, we're starting on page 19. This is the second derivative test. Suppose that our original function f of x is continuous. Okay, we've talked about that. It means that you can start your pen on the left-hand side and you can trace the entire graph without lifting it. There's no jumps, there's no asymptotes, etc. So, if the first derivative at c is equal to 0, okay, if there's a critical point there, and if the derivative at c is less than 0, second derivative, so we know then that the second derivative is negative when it's less than 0, we know then that it's concave down. Then x is equal to c at the location is a relative minimum. Okay, so we know that it's a critical point. We know that critical point again means that it's changing from increasing to decreasing or decreasing to increasing, and here it's concave down. So looking at would be something like, like this, right? And at this location there's going to be a relative maximum point, which makes sense. Similarly, if the first derivative equals 0, so it's a critical point here. There's a change in increasing to decreasing. And the second derivative is greater than 0, meaning it's positive, meaning it's concave up. Then, so we're looking at something like this, then at that location there's a relative minimum, which makes sense right there. Okay, let's move on. Let's think about that. So if the second derivative at 3 is greater than 0, that tells us that at 3 this is concave up. B, if the second derivative at the point x equals 3 is less than 0, that means it's negative. That tells us that at x equals 3 this graph will be concave down. C, the first derivative is greater than 0, so the first derivative is positive, meaning it's increasing. And the second derivative is greater than 0. It's also concave up at f. I meant to say at x equals 3, not f equals 3. Okay, D, we're looking here, the first derivative is equal to 0, so it's a critical point. It's where that point where it's changing from increasing to decreasing or decreasing to increasing. And the slope at that point is going to be equal to 0. And also at the second derivative, it's greater than 0. So we have a critical point there, and it's also a relative minimum. This is defined by the second derivative test. You can look back at that if you need to. E, we find the first derivative at 3 is greater than 0, meaning our function is increasing. The second derivative at 3 is less than 0, meaning that it's concave down. So it's increasing, and if we try to picture increasing and concave down, it would look kind of like this. And lastly, f of 3, we find it's a critical point at 3 from our first derivative. There's a 0 slope there. And the second derivative is equal to 0, meaning it's an inflection point. It's the point when the concavity changes from down to up or up to down. So what does that tell us? It's neither concave up or concave down. It's at a point of change. The slope is 0, so this is a critical point. We're a little unsure here if the function's increasing to decreasing or decreasing to increasing, because we know it's a critical point. So maybe it's looking like this, increasing. It's got there, I don't know if that looks like critical and inflection, that would be 3, or it's going from, it's decreasing and it has this curve here where it changes concavity and changes increasing to decreasing at 3. 2a is asking us to find where the first derivative equals 0. It's asking us to go back, what was that, 5.3, and find the critical points of this function. So I'm going to let you do that, finding the first derivative, analyzing those factors, probably using sign analysis to find the critical points, or where the first derivative equals 0. So we found that it's going to have critical points, or the derivative of x, f of x, equals 0 when x is equal to -3, or 2, or 0. I'm going to do sign analysis just to further show that. So the sign analysis shows that the function will be increasing here, although there will be this spot where it equals 0, and we'll look at the graph in a minute. We'll have a maximum here when it changes from increasing to decreasing, and we'll have a minimum at this critical point when it changes from decreasing to increasing. Here's the graph of the function, not the first derivative, just the function, and you can see that here is this critical point where it continues to increase. It increases until x equals 0, that's the maximum, and then it decreases until this minimum, that critical point where it changes to increasing again. So our first derivative analysis was correct. Let's use the second derivative test now to find, move this out of the way, to find the concavity and the relative extrema there. Okay, so you can find the second derivative. You're going to need a triple product rule, and then find those factors of the second derivative and do a sign analysis to find the inflection points and the concavity. Okay, here's the second derivative, and now let's do the sign analysis with those factors. You'll have to maybe do a little side calculation here to find what makes this factor equal to 0. Okay, so we can see now the second derivative is negative from -infinity till -3. Therefore, our function is concave down at that spot. We have an inflection point. You can write that word out, those words out if you want. And then, so that inflection point is when it changes concavity, and then it is concave up between -3 and -√3/2. Then there's another inflection point, and then it is concave down all the way to positive √3 divided by 2, where we have another inflection point, and then it is concave up. So the second derivative test states that where the first derivative is equal to 0, these critical numbers here and here, if we look at the concavity, so we see the critical numbers, and we did figure out that max and min from the first derivative. But if we look at the concavity, so now at 0 and at 2, that is 0 would be here. This is x equals 0, and x equaling 2 would be here. The second derivative test says then that if the first derivative equals 0 and it's concave down, that there will be a max at that point. And if the first derivative equals 0, which it did above, and it's concave up, then that will be a minimum. Okay, now here is the graph, and I believe that's shown to be true. So we have a maximum at 0, that's here, and a minimum here, a relative maximum and a relative minimum. Okay, let's look at the last. If you want to look in your books, this is on page 244, example number 5 at the top of the page. Okay, so what's given here is a graph of f of x. Okay, this is f of x. And we're supposed to fill in this chart here at each of these points. So f of x at point A, it's negative. Derivative then at point A, remember the first derivative tells you whether it's increasing or decreasing. So we see this function is going up, it's increasing. What about the second derivative at point A? The second derivative tells you the concavity, whether this curve is opening down or opening up. And in this case, it'd be opening down, negative. Okay, B, at this point. Now, we see that f of x at point B has a 0. It's where it's crossing the x-axis. The derivative, it's increasing at that point. And we still see that the second derivative would be negative. It's concave down. Moving on to point C, the first derivative will be positive. F of x is positive. The first derivative, again, it's increasing, positive. And our second derivative, that concavity, it's still negative. D, we see this very top peak. Well, the f of x, it's definitely positive. The first derivative, is it increasing or decreasing there? Neither, right? That's a critical point, the turning point where it changes. We see that has a value of 0. The slope at that point of that tangent line will be 0. The second derivative, the concavity at that point, is still negative. Point E, okay, we can see that the first derivative is, or the function is positive. The first derivative, the slope of at E will be negative, and concavity still opening down. Okay, I'd like you to continue filling in this chart. Of course, the answers are given to you on page 244 for you to check.